Hi, this is Terry Kushma here at Penn State University, and what we're going to go over today is part 5 in our series of carbon allotropes. And today what we're going to do in our history timeline, we're going to look at single-wall carbon nanotubes that were actually researched quite a bit in Japan at around 1993. So what we do is, this is the basic premise, that we take a look at all the different carbon derivatives. We take a quick look at each one. I imagine for each material like single wall carbon nanotubes, we could probably spend 20, 30 hours on one material and one application. But this is just a quick overview of carbon derivatives, so we hit the main points and move on from there. So we look at the discovery, then we look at the material properties, the manufacturing methods, and the applications. So in 1991, the first single-wall carbon nanotube were synthesized, and in '93, we look at the research that was done back in 1952 by the Soviets, and that was actually the first one. So it's arguable where the first carbon single-wall nanotube came from, but really we're going to use 1993 because these were purposely synthesized. So let's take a look at the discovery of single-wall nanotubes. So since 2006, the annual production each year has increased about tenfold. So we can look at a couple things that are good to look at when we review a different type of technology. We look at the amount of publications that were utilized in a particular year, and we also look at the number of patents that were issued to these particular units across the year. So as we can see, there's a tremendous growth as we go along in the years. The importance of the single wall nanotube is shown by this graph and the adoption by industry and manufacturing methods. So let's take a look at the material properties and the physics. So this is a list of different attributes that we get from single wall carbon nanotubes. So we look at the specific gravity, the elastic modulus, Young's modulus, the strength, the resistivity, the thermal conductivity, and the stability, and then the specific surface area. So this gives us the numbers to compare to other materials in that area. So when we look at the structure, we look at how these things are cross-linked together, and we see that these things have tremendous strength per unit area, and we also see that there's some random misalignment in these materials. And I think that's a theme looking at this entire note packet, that we often don't get a specific carbon nanoderivative. Often there's defects within these materials, and there's also a distribution of different materials in any manufacturing method. So I think that while these materials are very important, it's difficult in some level to manufacture them to a known consistency, to perfection, and to be able to get a tight Gaussian distribution of any particular carbon derivative. So let's take a look at some quick manufacturing methods. So like these are common to the other manufacturing that we saw for other materials like multi-wall carbon nanotubes, etc. We can use electrical arc discharge, and of course we use that for fullerenes. We can use laser ablation, which again is common in other attributes for making other carbon derivatives. We can use gas phase catalytic growth, and we can also use chemical vapor deposition methods. So we will, tweak these recipes to try to give us the best particular carbon derivative at that point, but we'll always get other carbon derivatives there, so filtration becomes a very big issue. So this is the system that we looked at initially for and is used in quite a few of the carbon derivative applications. This is the arc discharge method, where we actually arc the material from the anode side, and then we collect our growth species on the cathode. So this is the manufacturing method, and we can see on the far right, we apply the arc distance through that micrometer on the side, and we can also certainly control the ambient that's inside the machine, which is usually helium, and we can also control the pressure and certainly the arc energy along with the distance. So we can also look at other methods that we would use for manufacturing, the pulse laser beam method, and this is also used. The laser itself vaporizes a graphite target in a vacuum, and then a high temperature is used around 1200 degrees, and then we use a rod to collect and condensate the carbon on the tip, and then from that point we have to do filtration to the system. So this is a look at some of the carbon derivatives that we produced. So this shows from this paper down below that this actually gives us high uniformity and really good looking films. So the processes that we use for a single wall nanotubes, we can use a pulse laser to ablate a graphite electrode. The electrode might contain 1% of a cobalt nickel alloy. The vaporization occurs into a tube furnace at 1200 degrees C. The vaporization of materials carried downstream by an inert gas where it's collected on the outside of the furnace, and this produces a reasonable quantity of pure silicon wall nanotubes that have a good uniformity. So we can take a quick look at some applications. We can make composite materials, as we discussed before. So this adds along with the polymer base to give us increased stiffness and strength and toughness. And of course, these properties depend on the amount of material that we deposit into our composite and the ratio that we do, and the alignment that we do in dispersion of that carbon derivative within the material. We can also apply carbon nanotubes to microelectronics because they have a low electron scattering and around their band gap, and they can also be used as high K dielectrics in some areas. So this system takes a look. This paper down here can show you the review of these particular applications. We can also use biotechnology applications for carbon nanotubes. So a lot of times people say that they want to store biomolecules within these complexes and then be able to deliver the carbon nanotube inside the cell and then release things like DNA or biomolecules or proteins within the cell. So this has been shown in research, but I don't know if anything this is beyond the initial research stages as far as I know. So now let's finish our presentation and look at graphene. Graphene was really researched highly, or I guess went mainstream in the year 2004. So let's take a look at that. So again, as we did in the other past processes, we're going to look at the discovery, the material properties, and the manufacturing methods and the applications. So the existence of graphene has been noted for over 100 years, but the material itself was not appreciated until on that show till the year 2000 or so. Graphene is the basic structural element of other allotropes, including graphite, charcoal, carbon nanotubes, and fullerenes. So graphene was later rediscovered and isolated in the University of Manchester. So this work resulted in 2 winning Nobel Prize for physics in 2010, and these were groundbreaking experiments regarding the material. So now the global market for graphene is reported to reach $9 million by 2014, and I think that's a pretty long way from its initial status and discovery per se in 2004 and the Nobel Prize in 2010. So this is the discovery, and basically what we like to do, a lot of people do with graphene is they take graphite and they're able to delaminate that into sheets. So that's the basic process that people use. So let's take a look at material properties. So it's very conductive. It's a zero band gap conductor. It's very strong in that direction. It's 200 times stronger than steel. It's very flexible. It can stretch to approximately 25% of its length. It is 1 atom thick. It's transparent. with about 2% of light absorbed, and it's selectively permeable. So the conductivity in this material, it has 4 valence electrons, and it's a 0 band gap semiconductor, and the electron mobility is 15,000 centimeters square per volt per second in this unit. So this is some materials that we can look at the different applications of graphene that we can use, and this is certainly one of the derivatives of carbon. So we can see that we get 0-dimensional sheets. If we would fold this portion of a graphene sheet into a ball, then we get a fluorine. If we would take this portion of the sheet and fold it into a tube, we can get a single wall nanotube. And if we can peel off these sheets as individuals, then we're going to get 3D graphene. So graphene, a single layer graphite, is called graphene, and it has extraordinary electrical, thermal, and physical properties. The graphene image derived from an AFM is shown to the right. Graphene is formed as a 2-dimensional atomic scale honeycomb lattice, into which into each one forms a vertex. So this is the crystalline allotrope of carbon. It's very lightweight. It's 100 or 200 times stronger than steel. It's a perfect thermal conductor, and it has a bond length of about 1.42 angstroms. And we can see that bond length is related to strength. The bond length for diamond is about 1.54 angstroms. So graphene has many extraordinary properties. Like we said, it's very much stronger than steel. It has a thickness of about 3.35 angstroms, which is equal to the thickness of the graphene sheet. It conducts heat and electricity very efficiently. And then the global market is actually escalating as we speak. So the properties here, again, this shows us the Young's modulus and the tensile strength. And then we can look at the manufacturing methods associated with graphene. There are basically 2 types of manufacturing processes when it comes to isolating graphene. We can use mechanical cleaving and then chemical methods. The least expensive process is mechanical in nature, and it's known as mechanical cleaving to separate the carbon monolayers from the original graphene crystal. So mechanical exfoliation, which is repeated peeling from graphite, it can be produced by epitaxy on an insulating or conducting substrate. Applications include replacing silicon in high-performance electronic devices. So mechanical cleaving is very favorable when it comes to obtaining large 100-micron or so size, very pure monolayers of graphene. Note that this cleaving method is used by Geim and Noroslov in their Nobel Prize-winning research. And the disadvantage of this mechanical cleaving is large-scale production is very difficult to perform. It's difficult to be consistent in the exact amount of layers that are removed during this mechanical cleaving process. So chemical exfoliation uses common chemicals such as potassium permanganate or sulfuric acid to strip away thin layers of graphene. Although there are several different types of chemical exfoliation methods, the highest yield is the one that unzips the carbon nanotubes along the, with a methane plasma effect, giving a repair process. So this shows you the image of oxidized graphene layers, and they're like layers of paper. So this shows you, again, the graphene out of this link that you can go to down here below from Nature magazine. And this shows you the Raman shift of graphene. So this would give us the spacing of the material. And now we can take a look at some quick applications. Certainly we care about conductivity for things such as solar panel coatings to minimize the resistance once we collect the electricity in the solar panel. We can look to historically people made these by, I guess, happenstance in the Damascene blade. So taking iron, steel, and folding it over many times and beating it mechanically and heating it. What we did is we got the cross-linking the graphene sheets in there to give that steel strength. And then we could also use these graphene sheets to filter materials such as salt water. So graphene coated solar panels. So these are used, and you can take a look at this link for these applications, and used quite a bit in the University of China. We can look at these Damascus blades. So they looked at these different configurations of these knives, etc. And what people do is they basically take steel and keep on folding it over under heating, and then beating on the blade. And what it does is it knocks the excess carbon free, but it gives us that cross-linking of these carbon graphene sheets inside there, which give these materials incredible strength, especially for their time period. So they've been making these for hundreds and hundreds of years in different parts of the world. Again, for saltwater filters, what we can do is look at these graphene sheets, that they're permeable to water, but not permeable to the sodium in the material. So what it's able to do is leach out the water and keep the sodium in the other side. So again, that ends our presentation here for carbon derivatives. There's so many of them. I think the mainstay in this presentation has been to point out that it's very difficult to manufacture a specific type of carbon derivative. We usually get multiple carbon derivatives in any manufacturing process. There's a limited number of manufacturing processes, and basically what we do is try to control the performance values such as power, pressure, ambient, etc., to get a tighter Gaussian distribution of a specific carbon allotrope. And I think that we see the need for good filtration to get the carbon allotrope that was desired. So again, I think you should take a look at the links in here, because this was even at our condensed overview, this was a rather large presentation. So there's a tremendous amount of material to be looked at for each individual allotrope. So hopefully these links can help you out. So thanks for your attention, and we'll see you the next time in our discussion of nanotechnology. Take care.